Good morning, viewers. This is David De Los Reyes. It is February 8, 2022, and we are here in Los Angeles, California. Okay, my topic for this afternoon, guys, is the continuation of the integration involving hyperbolic functions. Okay. Let's proceed. Yesterday, I finished already two formulas under hyperbolic integrations. So for this afternoon, I will discuss four more because there are actually 8 integration hyperbolic equations. Okay, let's proceed with number 3. The number 3 formula for the integration of hyperbolic function is this. The integral of hyperbolic sine of b dv equal to hyperbolic cosine of b plus c. That's number 3. Number 4, later on I will give the derivation. Number 4, the integral of hyperbolic cosine of b dv equal to hyperbolic sine of b plus c. That's number 4. Number 5, the integral of hyperbolic tangent of b dv equal to natural logarithm of hyperbolic cosine of b plus c. Natural logarithm of hyperbolic cosine of b plus c. That's number 5. Number 6, the integral of hyperbolic cotangent of b dv equal to the natural logarithm of hyperbolic sine of b plus c. So those are 4 additional integration formulas plus the other 2 yesterday. So actually we got 2 more. The next time around I will discuss the last 2 more equations, okay? Then we could proceed with the evaluations of the integration involving hyperbolic functions. Okay, let's proceed with the derivation. For this number 3, we let y equal to hyperbolic cosine of x. Okay? From the exponential equivalent, hyperbolic cosine of x is actually e to the x plus e to the minus x over 2. Okay? We studied that from the previous discussions, okay? Taking now the differential of both sides. The differential of y is dy. Okay? The given exponential function, actually it got in denominator 2. And that is actually 1/2. It seems that the coefficient of the exponential equation is 1/2. So I bring it out. So this is 1/2 times the differential of the given 2 exponential functions. Okay? dy now equal to 1/2. Let's try to take the differential of this separately. It should be e to the x times dx, okay, plus e to the minus x times minus dx. We are following the differential formula e to the u du, okay, because the differential of e to the u is actually e to the u times du, okay. U for the meantime is x, so it should be e to the x times dx. Okay? Simplifying this, I factor out the x here. This is e to the x. This is plus, this is minus, so the second term will be minus e to the minus x over 2. That is after taking the differential. But if we try to recall the value, the equivalent of this exponential notation here, it is actually hyperbolic sine of x. This is hyperbolic sine. So dy now will be hyperbolic sine of x dx. Then take the integral of both sides. Okay? We are deriving the integration formula by using differentiation. Okay? And we are now integrating the integral of dy equal to the integral of hyperbolic sine of x dx. Therefore, the integral of hyperbolic sine of x dx equal to the integral of dy. I just rearrange, okay? This goes to the left, this goes to the right. The integral of the differential of y, this cancels out. Right, guys? So the right hand side will be y plus c. So but what is y? Y is hyperbolic cosine of x, right? So to bring out the general formula, okay, we will let x equal to b. Therefore, the integral now of hyperbolic sine of b db equal to hyperbolic cosine of b plus c. That's it. That's formula number 1. We just replace the value of x by b. So to arrive at formula number 1 to be more general, the integral of hyperbolic sine of b db equal to hyperbolic cosine of b plus c. Okay, guys? It's easy. That's formula number 3. So memorize this by heart. Okay, let's proceed with the derivation of formula number 4. We will derive this. Okay? I am checking my camera. For formula number 4, we will let y equal to hyperbolic sine of x. Okay? Y is equal to, in terms of exponential equivalent, it is e to the x minus e to the minus x over 2. For a cosine, this is plus, but for hyperbolic sine, the sine of this is minus, okay? Taking now the differential of both sides, we expedite a little bit, okay? Actually, this can be written as 1/2 times this, right? So if we take the differential of both sides, the differential of y equal to 1/2 times the differential of this. Two exponential functions. So they should be, the first one should be, the differential will be e to the x times dx, it is plus, minus e to the minus x times the differential of minus x, it is minus x, close bracket. Okay, simplifying. Factoring out the common factor dx, we got the dx here, we got the dx, I bring it out. Okay, this is e to the x. Sine of the second term will be, this is minus, so it will now be plus. E to the minus x over 2. But what is this? It is hyperbolic cosine, right? Therefore, dy now equal to hyperbolic cosine of x dx. Then take the integral of both sides. Then we rearrange. We put this one to the left, we put this one to the right. Therefore, the integral of hyperbolic cosine of x dx equal to the integral of dy. The integral of the differential of y is just y. Okay? So, the right hand side will now be y plus c. In terms of x, this should be hyperbolic sine of x plus c. And to bring out the general formula on how to take the integral of hyperbolic cosine of b db, we will replace x by b. Therefore, the integral of hyperbolic cosine of b db equal to hyperbolic sine of b plus c. That's formula number 4. Okay? It is easy because we are using the differentiation by using its exponential equivalent. Okay? So I told you before, the exponential equivalence is very important. Without knowing it, we could not proceed with the derivation. Okay, let's proceed with formula number 5. I am seeing your eyes, guys. Okay. Number 5. The integral of hyperbolic tangent of b dv equal to the natural logarithm of hyperbolic cosine of b plus c. This is under natural logarithm already. Okay? Okay, let's proceed with the derivation. We will let y equal to the natural logarithm of hyperbolic cosine of x. Y will be equal to the natural logarithm. Hyperbolic cosine is the plus sign, the sign at the middle is plus. E to the x, this is an exponent, right? Plus e to the minus x over 2. Under the laws of logarithm, we could simplify the right-hand side, simply natural logarithm of this exponential function here, minus the natural logarithm of the denominator, okay? The natural logarithm of a quotient is the natural logarithm of their difference. The natural logarithm of the numerator minus the natural logarithm of the denominator. Actually, even under common logarithm, we follow that rule. Under natural logarithm, it's the same. Okay, proceeding with the taking the differential. The differential of y is dy. If we take the differential of this, it falls under the natural logarithm of u. And it has actually du dx over u. Okay, that's one of the formulas under differentiation, right? So this is, our u is a combination of e to the x plus e to the minus x. So this is 1 over e to the x plus e to the minus x times the differential of these two terms here. Just be careful with your expansion because it's a little bit long. So this is multiplied by, open bracket, e to the x times dx. This is e to the u du, right? Plus e to the minus x. The differential of minus x is minus dx, close bracket. Natural logarithm of 2 is a pure constant. Taking the differential, it will be 0. So this is minus 0. Okay? If we now try to simplify, dy now will be equal to, this is an exponent, guys, e to the x. This is e to the x. This is plus, is minus, so the sign of the second term of the numerator is minus e to the minus x over e to the x plus e to the minus x, close quantity dx. Eye contact, guys. Okay? But if we try to take the equivalent of this under hyperbolic, that is actually hyperbolic tangent. Therefore, dy now equal to hyperbolic tangent of x dx. Then taking the integral of both sides, then try to transpose both the left and right quantities. We put this on the left, we put this on the right. Therefore, the integral of hyperbolic tangent of x dx equal to the integral of dy. This cancels out. Okay, right hand side equal to y plus c. But what is y? Y is natural logarithm cosine of x. Okay, natural logarithm hyperbolic cosine of x plus c. Indefinite integral. We do not know yet the value of c. So to bring out the more general formula on how to take the integral of hyperbolic tangent of b dv, we will replace x by b. Eye contact, guys. Okay? Therefore, the integral of hyperbolic tangent of b dv equal to the natural logarithm of hyperbolic cosine of b plus c. This is formula number 5. Right? That's formula number 5. Eye contact, guys. Last formula for today. The integral of hyperbolic cotangent of b dv equal to the natural logarithm of hyperbolic sine of b plus c. Okay, let's proceed with the derivation. I am right-handed, guys, so I always go to my right. We let y equal to natural logarithm hyperbolic sine of x. Okay, I will erase this one so it will be readable what I am doing. Y equal to hyperbolic sine is e to the x should be minus e to the minus x over 2. or this can be written as it's there. Y equal to quotient, logarithm of the numerator minus the logarithm of the denominator, natural logarithm. Okay? Then proceed with taking the differential of both sides. Same as for number 5. dy now is equal to 1 over u times du. The u here is a combination of two exponential functions, so this is 1 over e to the x minus e to the minus x times the differential of these two here. The first one will be e to the x times dx. Second one will be minus e to the minus x. The differential of minus x is minus dx, close bracket, okay? Natural logarithm of 2 is constant. Its differential is 0, so this is minus 0. Okay, simplifying. dy now will be equal to, first term is e to the x, it is this. I factor out the x. The sign of the second term on the numerator, it will be plus. This is minus, so this will now be plus. E to the minus x over e to the x minus e to the minus x. Eye contact, guys. Okay? But what is this? It is hyperbolic cotangent. Therefore, dy now equal to hyperbolic cotangent of x dx. The equivalent of this exponential equation is hyperbolic cotangent of x. Then taking the integral of both sides. Okay? Then we try to transpose the one on the right to the left, the one on the left to the right. Therefore, the integral of hyperbolic cotangent of x dx equal to the integral of the differential of y. This cancels out. Right? So the right hand side will just be simply y plus c. Plus c, it's indefinite integral. We do not know yet the value of c. But what is y? Y is natural logarithm of hyperbolic sine of x. So the right hand side will be natural logarithm of hyperbolic sine of x plus c. To bring out the more general formula on how to take the integral of hyperbolic cotangent of b db, we will replace x by b, where b could take any form of a function. It could be algebraic, exponential, other things. Okay, so actually we are bringing out a general formula for integration involving hyperbolic cotangent. Therefore, the integral of hyperbolic cotangent of b db equal to the natural logarithm hyperbolic sine of b plus c. That's formula number 6. I will check my camera again. Oh, that's it, guys. We finished for today. So memorize all these 4 formulas by heart, including the first 2 yesterday. That is the integral of hyperbolic secant square of b dv and the integral of hyperbolic cosecant square of b dv. We got 2 more. That will be our next topic for the next time around. Okay, then we could proceed with the evaluation of integrals involving hyperbolic functions. If there are some application problems, we will discuss it. If there is none, we will proceed with the other forms of integrations. So we could proceed with the application problems. Application problems, it's very interesting. The solution on how to take the area and volumes of irregular figures. Okay? Like the area of an ellipse, something like that. We will derive the formula on how to take the area of a circle. Why the area of a circle is pi r square, something like that. Right? Actually, the origination of that is from integral calculus. We will prove that the area of a circle is pi r square when we go with the application. Okay? That's it, guys, for today. If you like it, please click like. If you want to share it, please click share. Okay? If you want to follow my channel, please click subscribe. Thank you and good afternoon, Los Angeles.